Hello, welcome back to the second part of section 8.1, where we're talking about the sampling distribution of the sample mean, the mean of x bar. So the main result was what's called the central limit theorem. So in short, the central limit theorem said that if you have some distribution for some population, and no matter the shape, then as you take larger and larger samples, and you find the means for all those samples, the shape of the distribution of all those samples, that means the sampling distribution of the sample mean x bar, will become more normal. And we saw this with the example of the dye. Now, the central limit theorem can be divided sort of in two different scenarios. The first one is the distribution for x is already normal to start with, or it isn't. So central limit theorem says regardless of shape, but I'm going to divide it into the two different scenarios, when x is already normal and when it's not. So here I have the picture. So x is said to be normally distributed. Right? So I have a normal distribution for x. So this is what we call the population distribution. It's based on all the x values of the variable. Right? So it's based on the individual values of the people or the objects or the items. The mean is at the center, which is mu. And then the standard deviation, of course, is sigma. So the central limit theorem says that the sampling distribution of x bar will also be exactly normal. And for this one is regardless of the sample size that we pick. Okay? So from here, we're going to take some sample of any size. So the size doesn't matter. And so the sampling distribution of x bar will also be exactly normal. Now the mean, well, now it's about x bar, so now the mean is of x bar, and the standard deviation is then also sigma of x bar. So now here the values on the variable are no longer individual x's, but the means of the sample, so x bar values. Now, what if x is not normal? Well, we kind of saw the result from the example we looked at last time when we illustrated the central limit theorem. We had the example of a die where the die has a uniform distribution because each outcome has the same probability, right? So in this case, is uniform, which is not normal, right? But turns out that it doesn't just apply for uniform. It could be just not normal. So that means it could be any other shape. It could be skewed right or skewed left, or it could be complex, kind of all over the place. Or sometimes it's just simply unknown. You don't know the shape at all. But of course, there's always a mean, and there's always a standard deviation for this distribution. But since here the distribution is not normal, the sample size does have to be big. It has to be bigger than or equal to 30. So if x is not normal to start with, x bar will still be approximately normal as long as our sample size that we pick is large enough. So then the sampling distribution of x bar still normal. Of course, the center is still at mu of x bar, and standard deviation is still sigma of x bar because this is about x bar values. Right? Now, the distribution for x bar has a mean of mu of x bar, standard deviation of sigma of x bar. But how do you exactly find those values? Right? So to find those values, we are going to first, of course, we're going to know that we're going to grab some sample from some distribution with some mean mu and standard deviation sigma, right? And so the distribution for x bar will have a mean that is the same as that as the population, but the standard deviation is going to change. We're going to take the standard deviation of the population and we're going to divide by the square root of the sample size. So this standard deviation, sigma of x bar, is also known as the standard error of the mean. So instead of saying standard deviation of the mean of x bar, we call it standard error. Okay. Now z-scores can also be found for x bar. So to find z-score for x bar, you take x bar, subtract the mean, and then divide by the standard deviation of x bar, which is sigma over the square root of n, and that's what we find. We convert an x bar into a z. But to find probabilities, we're not going to be using z's. We are going to be using normal CDF, as we did back in section 7.2, because we are still dealing with a distribution that is normal. Right? So the sampling distribution for x bar is this normal curve, has a mean of mu, and has a standard deviation of sigma over square root of n. So if we're going to find some probability, now the probability is going to be about an x bar. So they're going to give us a sample, and then the problem is going to be asking about the mean of that sample. So that means the problem is going to be about x bar. So then to find the area, meaning to find the probability, all we have to do is normal CDF all over again. But keeping in mind that the mean and the standard deviation are now about x bar, right? And so mu is because we need the mean of x bar, which we know is just mu, and the standard deviation of x bar we know is sigma over the square root of n. Okay? So we have to use the mean and the standard deviation of x bar because we're looking at the distribution for x bar. All right, let's look at some examples. Look at this first one. Says a statistic instructor obtains heights of her students. The heights have a mean of 64 inches and a standard deviation of 4.6 inches and follow a normal distribution. She takes a random sample of 6 students. So before I get to part A and talk about what we need to find, let's summarize the information we are given. So let's read again. A statistics instructor obtains heights of her students. This problem is about heights. So it's going to be the variable of interest about heights. But we know that heights have a mean of 64 inches, a standard deviation of 4.6 inches, and have a normal distribution. So we do know the shape. And then from this distribution, she's going to obtain a random sample of 6 students. So that's going to be our n. So I'm going to summarize that information here on the side. So the distribution for heights will be the population distribution of the height, so in this case of x. And in terms of shape, the shape we know it's normal. At center, we know that would be the mean, which is 64 inches. And then the spread, we know is sigma, which is 4.6 inches, right? But then, so then let's look at part A. So part A says, describe the shape and center and spread of the sampling distribution for x bar. So now sampling distribution of x bar, right? So what about its shape? Right. Well, if the distribution is already normal to start with, then when we take samples, in this case our sample is of 6, since the distribution is already normal to start with, the sample size doesn't matter. So x bar is also normal. Its mean of x bar is the same as that of the population, which is going to be 64. And the standard deviation of x bar is the standard deviation of the population divided by the square root of n. So it's then 4.6 divided by the square root of 6. And I'm going to leave that in an exact form instead of having to round. And so this would be the answer. Sampling distribution for x bar is normal, mean of 64, standard deviation of 4.6 divided by square root of 6. That's it for part A. Let's look at part B. says, assuming that the requirements describing part A are satisfied, that means we have this information for part A. What is the probability that from a sample of 6 students, we obtain a sample mean of 67 inches or more? So now notice that the question is not about the sample mean. That means it's about x bar being 67 inches or more. So then we're going to answer this question using the distribution for x bar, not just simply heights, but the average of heights based on samples of 6. Right. So the sampling distribution of x bar, we know it's normal, has a mean of 64, and has a standard deviation of x bar of 4.6 divided by the square root of n. So now the value of interest is 67 or more. So let's find 67 somewhere on the right hand side, right? But it says or more, so we know we're going to shade to the right hand side. So the probability that the sample mean of those 6 students is 67 inches or more is equal to, well, we're just finding the probability under a normal curve, so that translates into a normal CDF. Our lower bound for the shaded region is 67. The upper bound will be, I think it's not going to fit in here, so let me go ahead and write it down here. Normal CDF, lower bound is 67, upper bound of 1E99, or you can use just 9999999. Our mean, remember, is the mean of x bar. This is about x bar, so this is 64. And we need the standard deviation of x bar because, again, this problem is about x bar. So it's going to be the 4.6 divided by the square root of n, and it shouldn't just be n, it should be 6 because our sample size is 6, right? So then we type this into the calculator, and you need, in the calculator, you'll be able to type in the whole 4.6 divided by the square root of 6 in the place of the standard deviation. So we should be fine. And you're going to obtain 0.0551. So that is that if a sample of 6 students was taken, then the probability that their average height of those 6 students is 67 inches or more is 0.0551. And this is our result, right? And so I'm going to stop right here.